Hello, everybody. This is Dr. Ekstrom, and this is the seventh, the last of the video lectures for our November 1 workshop on creating content-based digital games on the structure and energy of matter. And I thought I'd close out by talking about some unusual phase behavior that actually applies many of the principles that I've discussed in the previous videos. And I may bring this out earlier in the actual workshop, but I think here for the videos is a good way to wrap things up. And so I want to first talk about two frozen solids. So what happens when you heat, excuse me, when you heat frozen water? So frozen water is ice. What happens when you heat it? Well, hopefully your students would say it melts. And so this melting is the phase transition from a solid to a liquid. Now, what would happen if you take frozen carbon dioxide and heat it? So here's some frozen carbon dioxide. It's actually available, I know in Kearney, at least one grocery store, I think, carries it. Well, what you'd find is it seems to disappear. It actually does not melt. It does not go from a solid to a liquid. Instead, it goes directly from a solid to a gas. We call this process sublimation. And of course, I'm sure that you know, and many of your students know, that frozen carbon dioxide is known as dry ice. And so the dry ice term comes from the fact that again, the frozen carbon dioxide does not melt, but it sublimes instead. Interesting. So we consider that pretty unusual phase behavior. Here's another one. Who wants to put a soda can in the freezer? I don't know if I'll do this at the workshop or not. But if you take a soda can and a perfectly normal looking soda can full of soda, put it in the freezer. After a few hours, you open the freezer back up and you may see this. The cans burst open. Why does this happen? Well, it turns out that, of course, the soda, it consists mostly of water, and it turns out that water expands when it freezes. It turns out that property is actually very unusual among substances in nature. So, one other property. Why is ice skating possible? And I don't know how many of you think about this, but when you think about direct contact between the ice skating blade and the ice, uh, it turns out that there is actually no direct blade ice contact. In fact, if there was, it would be much, much more difficult to ice skate. In actuality, a thin water layer forms between the blade and the ice. How on earth does this happen? Well, here we need to start going into some more deeper explanation. I'm going to talk about phase diagrams in this video, and phase diagrams can help us understand these types of behaviors that I've been talking about. A phase diagram is a plot of pressure and temperature for a given substance, and so and then you draw in lines where you have phase transitions. So we note where solid, liquids, and gases are the most stable. So here you see a generic phase diagram on the right. And so there are three regions and 2 points noted. We've got a region where solids are stable, a region where liquids are stable, and a region where gases are stable. And it's always the same order. It's always solids to the left, gases to the bottom, and then liquids in between. Okay, now the 2 points, first we have a triple point. The triple point is where the solid, liquid, and gas boundaries all come together, and it's the one pressure and temperature where all these three phases can coexist equally, and in fact you can't distinguish between them. So I mean they would all appear as the triple point. At the triple point, all three phases appear to be the same. Now the other point is over on the right, the critical point. You notice that the gas-liquid boundary stops at this critical point. The solid-liquid boundary kind of goes on infinitely. But when we reach this critical point, if we go to higher pressures and temperatures than the critical point, then the compound can exist as another type of fluid that we call a supercritical fluid. And it's, again, it's kind of its own phase, very interesting and very useful. Because they can be used as chemical cleaners or dryers, and in fact, they work great in that process as that. And in fact, carbon dioxide is actually the most common supercritical fluid used industrially, and we actually use it at UNK when we're making aerogels. The final drying steps are done using supercritical CO2, and the reason for this is that you dry the sample of CO2, and then in the dryer, of course, you have to have higher pressures, higher temperatures. When you bring these conditions back to normal, the fluid just evaporates. And so it's a very clean way of drying substances. And so here in this picture, you've got just some pictures of some liquid carbon dioxide gradually converting to the supercritical phase. And when it's in the supercritical phase, you can't distinguish it from air or liquid, but it is a fluid. And like I said, very effective in industrial cleaning and drying. So let's go back to one of the situations I talked about earlier. Why does dry ice sublime? So in order to understand that, we need to have the phase diagram for carbon dioxide, which we have here on the slide. So subliming means we are going directly from the solid phase to the gas phase. And the reason this is possible in CO2 is because liquid CO2 can only exist above an atmospheric pressure of 5.1 atmospheres. Okay, so you notice liquids can only exist at pressures above that of the triple point. The triple point pressure for CO2 is 5.1 atmospheres. We live life around 1 atmosphere pressure, so we're right there. So you notice, if you are on the 1 atmosphere pressure line and you take dry ice and you increase the temperature, that means you're going left to right on the phase diagram. So going left to right in the phase diagram, what eventually you do is you eventually cross the solid boundary, but instead of going into the liquid phase, you go directly to the gas phase. So that's why dry ice sublimes. How about the ice skating situation? Well, in the ice skating situation, we need to look at the water phase diagram. And with water, in ice skating, what's happening is we are applying pressure to the ice, and that pressure is what is melting the ice. So you ice skate when it's cold in an arena or outside. And so now this time on the phase diagram, we are staying at the same temperature, but going up. We're increasing pressure. And eventually what happens is when you increase pressure, you cross the solid boundary and go into the liquid phase. This is very unusual among compounds. I mean, really, and basically the big difference is if you look at this boundary, the solid liquid boundary in the water phase diagram, the slope is negative. That is very, very unusual. For almost all compounds, that slope is positive, like we saw in the carbon dioxide phase diagram. So one thing that's true, and I don't know if you're an avid ice skater, you may know this, that the temperature outside actually can affect the quality of skating. The colder the temperature, the more difficult it is to ice skate. And that hopefully you can figure out why that's the case using the phase diagram. The colder it is, the more you're moving to the left on the phase diagram. That means the more pressure you have to apply to get that good liquid film between the skate blade and the ice. And so the ideal temperature to skate is just under freezing. You'll get your best ice skating, your most glide. All right. And then lastly, why does water expand when it freezes? We don't need a phase diagram to explain this, although actually it does relate to that slope of the solid liquid line. Here, though, I think it's easier to think about the hydrogen bonding properties that water has. And so when water's in the liquid phase, there's lots of hydrogen bonding going on, but the water molecules have enough energy that they still continue to flow over one another. And so hydrogen bonds between individual molecules are constantly being broken and reformed and rearranged. But when you freeze the water, the molecules they no longer have the energy to flow. So what happens is that the hydrogen bonds get locked into place, and there are particular six-membered ring structures that are the most stable. Well, these six-membered ring structures take up more volume than liquid water takes up. And so therefore, when water freezes, it'll actually expand to adopt this new fixed rigid hydrogen bonding structure. And that's why if you have water or soda in a can or a bottle, it could end up with the bottle or can rupturing. So that's the last of our 3 unusual phase behavior cases. I hope you and your students enjoy that. And that concludes our videos associated with the November 1 workshop. So I will see you at the workshop.